So that's when we're going to talk about the unit circle, which is exactly what it sounds like. It's a circle with a radius of 1 unit. So when we do a unit circle, we start at the center, 0, 0. And it's a normal XY graph. That's what people tend to forget. It's just a normal XY graph, and it's just you have a circle with a radius of 1. So you go 1 to the right, and you get the point 1, 0. And you go 1 up, 0.01, 1 to the left, negative 1, 0, and 1 down, 0, negative 1. It's like a normal XY chart. So that's the unit circle. Now we use the unit circle to find measurements of angle. So what we do is we start at the x-axis. It's like 0 right here. That's where we start. And then if we want a positive angle, we go counterclockwise or anti-clockwise. So we go this way. If we have a negative angle, we go clockwise. For example, if I want you to graph, let's say 120 degrees, draw a normal XY chart. We'd start at 0. A full circle is 360. So if you go around a full circle, it's 360. Halfway between 0 and 360, right here would be 180, half of a full circle. Halfway between that would be 90 degrees. Also, because it's an XY chart, so it's perpendicular. And then it basically goes 0. We add 90 to get here, add 90 to get here, add 90 to get here, to make that 270. Add 90 to get 360, and then you can keep on going around. If I wanted to plot 120, it's a positive angle, so we're going to go up. And you just got to get the right quadrant. So we want between 90 and 180, so we're just going to be over here. Somewhere over here. This will be 120 degrees. That angle right there. 120 degrees, about. So that's how we plot angles. Positive you go up, negative you go down. Now let's talk about reference angles. Reference angles are just the angle between what we call the terminal side, like our angle here, like that's called the terminal side. The terminal side of our angle and the x-axis. X-axis being the key. We're always going to go to the x-axis. We say when we draw a picture like this, we'll draw like here's our angle. This is the terminal side. We're always going to go down to the x-axis to make a right angle. And then this right here will be our reference angle. It's a very important concept for the unit circle. It's like the one we did right here, right? Our angle is 120. Make a triangle kind of with the point straight down. And this is our reference angle. In this case, we can actually find out what it is. This is 120, this is 180, so they're 60 apart. So that's a reference angle. It's just the distance from the terminal side of your angle and the x-axis. X-axis being the key. We always go down to the x-axis. Alright, so again, this in general. We'll do a few examples. If I want you to draw, like, let's say we're going to do an 80-degree angle. Pretty self-explanatory. You have 0, you have 90. So 80 would be somewhere over here. So we always go straight down to make a right angle. And the reference angle here would just be, anytime you're in the first quadrant, it's actually just the angle. Because remember, 80 is the angle from here to here, is our 80. So in this case, my reference angle would just be 80. Like that. Now if I use something else, like let's do a reference angle for 100 degrees. So here's 0, here's 90. Here's 180. 100 would be somewhere between 90 and 180. Again, it doesn't be, you don't have to be perfect. But a lot of times I just go straight down the middle because I just want to know what quadrant you're in. But if we're trying to be a little bit more accurate about it, about there's 100. There's 100 degrees. Right? Now the reference angle just goes straight to the x-axis. So do something like this. And then this will be my reference angle. Right? Reference angle is always the one next to the origin. So it's the angle from the side to the x-axis. In this case, this is 100 degrees. This is a 180. So we're 80 away. And that's my reference angle. So let's do a few more. Because it is, again, a pretty big concept in the unit circle, no matter which way you do it, for most part. So let's graph 300. So 0, 90, 180. These are all degrees. You know, I don't say it. Then 360. Right, so 0, 90, 180, 270, 360. I can keep on going around, by the way. Just keep on adding 90. Keep on going around. But 300 will be a little bit past 270, and not 360 yet. So in this quadrant 4. By the way, remember quadrants are 1, 2, 3, 4. So we have more important later. So we go there, we always make a angle with the right angle. Right angle with the right x-axis, and this will be my reference angle. All of this was 300. Now, honestly, for the sake of it, I don't generally write that. I'll just put a line right here that lets me know, oh, we went 300 degrees. Right, that lets me know I went from all the way there to there. This is 360, that's 300. So this would be 60 degrees. That's my reference angle. 115, last one, before we move on to other things. So here's 0, here's 90, here's 180, here's 270. 115, I guess, is in quadrant 2. Somewhere in quadrant 2. 115. And again, we have to go down to the x-axis. And then this will be my reference angle. 180. Okay, so again, all this is 115. And 115, 180, subtract them. And I get you about 65. So 65 degrees is my reference angle. So that's how you do reference angle. Very important part of the unit circle. Next up, how do trig functions relate to the unit circle? When I'm talking about trig functions, I'm talking about SOHCAHTOA. So remember that sine, cosine, and tan. Sine of an angle is opposite of hypotenuse. Cosine of an angle is adjacent of hypotenuse. Tan of an angle is TOA. Tan, opposite over hypotenuse. TOA. Opposite or adjacent. I don't know why I said hypotenuse. So what's going on here is this, we're going to talk about how this relates to the unit circle. So here's my unit circle. It's a little blurry. If I pick any point on the unit circle, we'll just call this XY. What do? Well, we always do the same thing. We always go from the origin to that point, and then we go straight down to make a right angle. Like that. Now, remember what I said? We're going to relate this to the reference angle. A reference angle is always this angle right here. So we're going to call that theta. So when we do a unit circle, again, it's always the inside angle because that's your reference angle. When we do a unit circle, we always reference to the inside angle. So here's my reference angle. There's that. Now, this is a unit circle. So that means my hypotenuse here is 1. That's your radius, 1. I don't like that color. So that's 1. Now, what's the opposite here? And what's the adjacent? We have a point XY. So x is how far you go on the x. So this will be x. And y is how high you go on the y. Y is like the y value, so how far up and down you go. So this is y. Right? And if I want to do my 3 trig functions of this triangle here, it's just going to be, here's my angle, so opposite, adjacent, hypotenuse. So sine is going to be opposite over hypotenuse, so y over 1, or just y. Cosine of a unit circle, so it's going to be adjacent over hypotenuse, so x over 1, or just x. And then tan is TOA, so it's opposite of adjacent, it's y over x. And that comes to our first little thing. When we have a unit circle, if you know the points, sine is always the y value, cosine is going to be the x value. I wrote that funky. And tan is y over x. What I do a lot of times, since y is sine and tan and x is cosine, I just use the fact that tan is sine over cosine, which is actually a trig equation identity. Now, so we got to remember that sine is the y value, cosine is the x value. Now, that only works when we have points, which is one way we could do this, and we'll talk about that later. But anytime you have it land on a point, sine is the y value. On a unit circle, sine is the y value, cosine is the x value. How do I remember that? I always say sine. It's dumb, but it works for me. Sine is the y value. Cosine is x. So sine. So let's use that. Let's talk about quadrantal angles. Quadrantal angles are angles that fall on the axes. So what do I mean by that? I mean by that stuff like this. I'm going to say, what is sine of 90 degrees? Or I could say, what is cosine 180 degrees? Or I could say, what is tan of, let's go 180 degrees? And then let's also do tan of 270. So what happens here is I'm going to say, what's the sine of 90? So we got to know that 90 degrees, here's 0 degrees, 90 degrees is up here. But it's on the line. So it's like this point right there. So how do I do that? Well, don't forget, it's a normal graph. It's a unit circle. You went up 1. This point is 0, 1. If I went to the left here, 180 degrees, that point would be negative 1, 0. Down here at 270, that point is 0, negative 1. If you go to 0, that point is 1, 0. So at sine of 90, I'm up here at 90, then we just got to remember, sine E, sine's the y value. Right, sine's the y value, so it's just 1. Right, we got to remember sine is the y value, cosine is the x value, tan is y over x, also known as sine over cosine. Most of them actually go opposite, so tan is sine over cosine, which is y over x. Anyway, so same thing with cosine of 180. Well, where's 180 at? Right here. Cosine's the x value, so the x value there is negative 1. Let's do tan of 180, same spot. Now remember, tan is sine over cosine, so this is actually how I think. I go tan is sine over cosine, so I know. So that means that it's y over x, because sine E, cosine x. So what's the y value here? 0, and cosine is negative 1, so I just get 0. Tan of 180 is just 0. Tan of 270? 270 is down here. Right, so same idea. It's going to be y over x. In this case, it's negative 1 over 0. You can't divide by 0, so it's undefined. So that's how we do trig functions when it falls on a quadrant triangle, when it falls on a line. That's what we do. You go, okay, it falls on a line. I know what these points are. Sine is y, cosine is x. Just find out your values. So what happens when it doesn't fall on the line? Well, that's when we have different options of doing it. Now, my preferred way is using triangles, and specifically special right triangles. So if you remember your special right triangles, we have 30, 30, 60, 90. And 45, 45, 90. Now, to me, I actually just treat them like 3 separate triangles. Instead of being 2 triangles, I treat them like 3 separate triangles. Those are some terrible degree signs. There we go. So I'll treat this like a 30-degree angle. That's all I really care about is the 30 part. What happens when that angle there is 30? So instead of being 2 triangles, I think of it as 3 triangles, which I think actually makes it easier. So if this is 30, 30 is a small angle, so it gets the 1. The right angle there. Hypotenuse is always 2. And then my adjacent side would be rad 3. Alright, so if in a 30-degree triangle, 30 is a small angle, so opposite it's a 1. Hypotenuse is always 2. And then my adjacent, rad 3. So what happens if I have a 60-degree triangle? Right, both of these triangles are 30, 60, 90. Well, 60 is the big angle, that's how I remember it. 60 is the big one, so opposite is the rad 3. Hypotenuse is always 2. Notice how they're always 2, and that means my small side is 1. So right, they are the same triangle. So you just gotta know which one goes with which. 30 is small, gets the 1. 60 big gets the rad 3. How about when I go 45, 45, 90? Well, the key there is keep in mind it's an isosceles triangle, right? 45, 45. So if this is 45, the other one's 45. So the sides have to match. So we just call that 1 and 1. Hypotenuse is always 2, but in this case it's a radical 2. So 1, 1, rad 2. So for me, if you want a couple of tips, hypotenuse is always a 2. Right, so sometimes it's radical 2, sometimes it's just 2. But it's always a 2 in the hypotenuse. You should only ever put a 2 in the hypotenuse of a special right triangle. Also, there's only ever one radical. Right, so it's either rad 2 or rad 3. Right, you never have 2 radicals. So that's why for me, when I go, oh, 60 is rad 3, then this has to be regular 2. Over here, you have 1, 1, 2, it has to be a radical, so that's going to be radical 2. So I just use those 2 in my head to like keep things straight of which one goes where. And then also for the rest, I just think 30 is small, so it gets the 1. 60 is big, it gets the rad 3. Like, that's how I think about it. So for me, in my head, it's like, oh, 30 is small, it gets the 1. 60 is big, it gets the rad 3. Right, and then 45 just thinks it's an isosceles, so it's 1, 1, and then rad 2. So with these special right triangles, with the reference, the quadrant triangles, knowing those, with knowing the reference, SOHCAHTOA, and knowing the reference angles, finally got there, I could figure out trig functions of most things. So we're going to use reference angles, we're going to use SOHCAHTOA, and we're going to use our quadrant angles, and they fall in that spot. And we'll use the special right triangles to find trig functions of most things. So I call this the triangle way. So the first way I'm going to show it to you. This is my favorite way. It's the way I do it. Because once you get really good at it, I just build triangles in my head all the time. Maybe that's just me though. So how do we find trig values of any function? Well, not any function, of most functions. So step 1, graph the angle in standard position. So generally when I do this, no matter what, that's the first step. You're going to graph the angle in standard position. That's just graphing it we did earlier. We'll do it again here. And then we make a right triangle with a reference angle. So I'm going to do this these two I'm going to do it like every single time. Like this thing never changes. No matter which way you do it, that's just the thing you're gonna have to graph the angle in the standard position. You're gonna have to make a right triangle with a reference angle. Now when you get better at it, you can just do it in your head, but that's always the first 2 steps. First 2 steps for me when I do it. And then since we're doing the triangle way, this is what's special to the triangle way. These last 2 steps is once you make a reference angle, it's gonna be one of the special right triangles. It'll be a 30-60-90 triangle, it'll be a 45-45-90 triangle. So you fill out the sides using those 2 triangles, and then you use SOHCAHTOA to get the value. And like we talked about before, if you happen to fall on the quadrant angle, if you happen to fall on the line, then it's one of the special values. And remember that sine is y, sine e, and cosine is x. And then tan is sine over cosine, which is y over x, because sine is y, cosine is x. So if you happen to fall on one of the quadrantal angles, then it's just, what's the point? Sine is y, cosine is x, tan is sine over cosine. So let's do an example. Evaluate sine of 60. So step 1, draw it. Right, here's 0, here's 90. So 60 is in between these two somewhere. So 60 degrees. And then we always do the same thing. We make a right triangle with the x-axis. With the x-axis, very important. Our reference angle is always the inside one. Now in quadrant 1, this is going to be a reference angle. So you just went up 60, so this is 60. Now again, if we're doing a triangle way, now we have to have the stuff memorized. What are the sides? 60 is the big one, so opposite is rad 3. Hypotenuse is always 2, makes my adjacent 1. So now I got to find sine of that. Sine is SOHCAHTOA. I should say sine is so. So is opposite over hypotenuse. Right, if this is my angle, opposite's over here, and my hypotenuse is over there. So I get rad 3 over 2. And that's the answer. Sine of 60 is just rad 3 over 2, right? So I draw my angle. 60 is a big one, gets to rad 3, hypotenuse 2. Sine is opposite, so to me that's my favorite because it makes it easy. It's opposite at 60, rad 3, over hypotenuse 2. Cosine of 135. So we draw it 0, 90, 180, 270. I guess I don't need to go as far. 135 is between 90 and 180, so 135 would be in here somewhere. Right? We always draw a right angle with the x-axis. We find a reference angle. 135 and 180, subtract them. 180 minus 35 is 45. Now, there's really only going to be 3 options. It's going to be a 30, 60, or 45 degree angle. That's all it is, because we're only doing the special right triangles. And again, now it's 45, I should know my sides. So it's an isosceles triangle, so 1, 1, rad 2, right? It's an isosceles, so 1, 1. Hypotenuse is always 2. In this case, it's a radical 2, because these are both 1s. So I get this. Now there's one special thing I kind of skipped, which is, don't forget it's a normal XY, it's a normal XY graph. So in an XY graph, if I just said like plot it, you're like 1, 2, 1, 2, negative 1, negative 2. Why are those negative? Because you went to the left, right? If I went down, negative 1, negative 2, because you went down. So it's like the same thing. If you go to the left, it should be negative 1. I went up, so a positive 1. If I go down, it's negative. If I go right, it's like it's a normal grid. So it'd be positive here, negative here, and negative here. Right, like a normal grid. Up is positive, right is positive, left is negative, down is negative. The one thing I would say, hypotenuse, we'll talk about this more. Hypotenuse is always positive. It's because it's a distance, we consider it. So distance is always positive. So hypotenuse is always positive. Anyway, so I get this. This is a negative because I went left. We're doing cosine, so ga toa, so adjacent over hypotenuse, -1 over rad 2. And you can leave it like that, or if you want, you could rationalize it. So rationalizing is also very popular. So you multiply by rad 2 over rad 2, which will get you negative rad 2 over 2. So again, both of these are okay. -1 over rad 2 is fine, or negative rad 2 over 2 if you want to rationalize it. And again, why is it -1 over rad 2? Because cosine is adjacent. So adjacent, this is opposite to 1, adjacent here, hypotenuse there. Tan of 210, we can do some more. Right, so here's 0, here's 90. I'm going to go a little faster now. Here's 180, 270, 360. 210 would be somewhere between 180 and 270. So it'll be in here somewhere. So there's 210. Draw a right angle with the x-axis. Draw your reference angle. Figure how far apart they are. This is 210 and 180, so this should be 30 degrees. Again, once you have that, you just have the size memorized. It is 1, because 30 is small, so opposite to 1. Hypotenuse is always 2. And then this makes this rad 3. Right, there's always one radical. So in this case, it's rad 3. Just like I thought before, keep in mind it's an XY chart. I went to the left, so this should be a negative rad 3. I went down, so it should be a -1. So it's like a normal XY chart. Hypotenuse is always positive because it's a distance, so that's just positive 2. Now we're doing tan. Tan is toa, so opposite over adjacent. -1 over negative rad 3. Oops. So just 1 over rad 3. Again, that's fine. If you want to rationalize it, you can multiply both top and bottom by radical 3, and you would get rad 3 over 3. Also new. So either way is fine. Cosine 330. 0, 90, 180, 270, 360. 330 would be somewhere between 270 and 360. So like that. Right, we always go to the x-axis. There's our angle, right? Reference angle is always so right. Keep in mind, we always go to the x-axis. Reference angle is always the inside one. This was 330. Right, we went all the way around to 330. So 330, 360. How far apart are they? They're 30 degrees apart. And once you know that, just like it's the same side. There's only 3 options. So this is 1. Hypotenuse is always 2. This is rad 3. Keep in mind, so it has to be negative. Well, some things might be negative. We went to the right, so that's positive. We went down, though. So -1. Hypotenuse is 2. So now we have to do SOHCAHTOA. Ka, adjacent over hypotenuse. Remember, wherever your angle is, opposites when one right across from it. Hypotenuse is always the opposite right angle, and adjacent is the left over 1, the one next to it. So adjacent would be rad 3, hypotenuse would be 2. So I circled the wrong one. There we go. So I get rad 3 over 2. Next two, sine and tan. Sine of 90 and tan of 270. So sine of 90, here's 0, here's 180, here's 90. So keep in mind, I fell on a line, so it's a quadrantal angle. So the way I do it, anytime I fall on a line, just know the point, right? It's a unicircle. We went up 1. So it should be 0, 1. We're doing sine, sine. Sine's the y value. So the answer here is just 1. Right, so anytime it falls on a point, we just go, okay, x or y. Which one am I doing? Or am I doing tan, which is y over x? Next one's tan of 270. 0, 90, 180, 270. So down there, that is 0, -1. Tan is sine over cosine. So it'd be y over x. So in this case, that's -1 over 0. You can't divide by 0, so this is undefined. Tan at the y-axis is always undefined. So if you have 10 at 90 or 270, it's always going to be undefined because you can't divide by 0. So that's doing a unicircle using the triangle method. It's the way I do it. It's the way nowadays I don't draw it by hand. I just draw it in my head. But that's one way of doing it. And if you put it all together, like every single possible special right, you get the full unicircle, which is this thing, right? It has every single special right triangle, 30, 60, 90, 45, all the different sides. You see some radians, we'll talk about that more later. And then each point. So if you look at this, like, let's say this 30 right here, right? If I was trying to find a reference angle for 30, you do this little triangle here, 30 degrees. That point right there is rad 3 over 2 and 1/2. You might wonder, like, all the ones we did, are some of the ones like my radius was 2. That's not a unit circle. That's not a unit circle. Well, it's because the ratios are still the same, right? My ratio here at 210 was 1 over rad 3. If you look at right here, right, this on a unit circle, my radius is 1, but my x value here is rad 3 over 2, and my height is 1/2. So if I did sine, I would just get 1/2 over 1. Same thing as, so the ratios are the same. You know what? When I do a triangle, it's not actually a unit circle, but the ratios are the same. It keeps the same. It's a similar triangle, so it still works. So that's why it works, because it's the same. Just a bigger triangle. Anyway, that's the full unit circle. And like I said, I do this by doing right triangles in my head. One way to do it though is to memorize the unit circle. Some people do it that way. They just memorize that whole thing. You can do it. There's not that many different patterns. It's always the same answer, just negative or positive. That's a little much for me. Again, I personally do the triangle way. That's a pretty bad part, but I do love it. That's slightly better, I guess. Another way people tend to like it is the table method. This is a little bit more memorization. You just build a table every time and you just kind of reference it. So let me go over the table method. In table method, we do sine theta, cosine theta, tan theta. And what we do on this side is all the possible main unit circles. So we have 0, 30, 45, 90. So 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And then sine, always put down the sine value. So it's just a memorization. Sine, if you look at here, it's sine of 0 is 0, so y value. Then it's 1/2. Just look at the y values, right? Sine is y. Rad 2 over 2, rad 3 over 2, and then 1. Right, so it's just memorization. Sine is 0, 1/2, rad 2 over 3, rad 3 over 2, and 1. It's actually not that bad to memorize. It's just like 0 over 2, 1 over 2, rad 2 over 2, rad 3 over 2, and then 1. Where does that come from, by the way? This is rad 0 over 2, which is 0. Rad 1 over 2, which is 1. Rad 2 over 2, which is 2. Rad 3 over 2, which is 2 over 2, which is that. And this right here is actually rad 4 over 2, which gets you 2 over 2, which gets you 1. So that's what's going on. It's just this thing over, rad this thing over 2. But anyway, most people just memorize it. They don't care about that part. Cosine, all you do is flip it. It's 1 rad 3 over 2, rad 2 over 2, 1/2, and 0. Alright, so we just flip it upside down. And then tan, remember what I said, tan is sine over cosine. So we'll just put sine over cosine. So 0 over 1 is 0. 1/2 over rad 3 over 2, the 2's cancel out, it's just 1 over rad 3. Over here, they're both the same, rad 2 over rad 2, which is 1. And then over here, rad 3 over 2 and 1 over 2. Again, the 2's cancel out, you just get rad 3. And then 1 divided by 0, you can't do that, it's undefined. So that's the table. Now, when you do a table, you can't just only do the table. You have to because when you do, what happens when we get to over there, right? We still got to draw it, and we still got to find the reference angle. And there's one more thing. How do we get the plus and minus? Now, that's something I kind of skipped earlier, but a shortcut to find the plus and minus, so anyone could do this, is this. ASTC. This is called a sign chart. So I guess it's a positive sign chart. It lets you know where things are positive at. So A stands for all, S stands for sine, T stands for tan, C stands for cosine. So this is saying, this is letting you know where all the trig functions are positive at. So let's break it down one by one. So if I was doing sine, where is sine positive at? Well, it's positive at A because all of them are positive at A, quadrant 1. And then sine's also positive at S. That's what that stands for, sine. So if it's positive at these two, it must be negative at the other two. So that's the sign chart. Also keep in mind, sine is the y value, right? Sine's y. So when you go up, sine's positive. That's why it's positive up here. When you go down, sine's negative. That's why it's negative down here. How about cosine? So where's cosine positive? Cosine is positive at the A, because all of them are positive at the A, and at the C, because C stands for cosine. So plus here and here, and it'll be negative at the other two. Also keep in mind, right, cosine's the x value. Where's x positive? To the right. That's why it's positive here, and it's negative to the left. That's why it's negative here. Tan, right? Tan is positive at the a because they're all positive at the a, and at the t. That means it must be negative here and here. And then why does tan work that way? Well, tan, remember, sine over cosine. So this is plus over, so it's like plus divided by plus is plus, and then negative divided by negative is positive, and the other two are like a mixture. So that's why they're negative. So that's how you read the sine chart. Instead of writing all three of these down, we just write this one. So I know, oh, I'm in quadrant 3, only tan's positive. Oh, I'm in quadrant 1, all of them are positive. That's the way this works. So let's practice a little bit using the table. So I should probably write down the steps for the table. 1, if you want to do the table, it's still draw it. Draw the angle. 2, right, find the reference angle. 3, use reference angle with the table to find value. And then 4, use AES, I haven't said the acronym for this, TC, to find sine. A shortcut to remembering ASTC is, well, the one that most math teachers use is all students take calculus. So ASTC. Some people use, like, I don't know. All students calculus is the one it's the industry standard. I think one of the books says all sea turtles crawl, or all sea turtles crawl. Whatever you want. I just generally use all students take calculus. So that's the steps. So let's do like 225. Let's do these two problems, right? So tan of 225. I'm still going to draw it. 0, 90, 180, 270, 360. 225 would be in here somewhere. So let's draw a line. 225. We still go down to the x-axis, or up to the x-axis in this case. Our reference angle is still this corner right there. And then you do 225 minus 180, which will get you 45 degrees. And then 45 degrees for tan. We look at our table. Tan of 45 is 1, right? Here's 45, here's 10, so it's 1. Last thing I do is I check all students take calculus, see if it's plus or minus. All students take calculus. We're in the T1, so we are positive, right? So we're doing tan, tangent T, positive. How about cosine 150? So 0, 90, 180, 270, 360. So 150 will be in here. So again, we always go down to the x-axis. There's our angle. This is 150. So they are 30 degrees apart. Here's 30. Now again, so if you're doing the table method, you don't have to memorize the triangles, but you do have to like write down the table and use it. So all we're gonna do is go cosine of the reference angle 30 degrees. So here's 30 degrees, here's cosine, so rad 3 over 2 is our number. But then don't forget the last step is check your sign. And this part, the check the sign part, you could do, if you do the triangle, you just don't like the negative part of it, you can still do this. This works for everybody. I should say this part works for everybody. All students take calculus. We're in quadrant 2, so only sine is positive. We're doing cosine, so my answer should be a negative. So that's the way that works. The one here is 180. So this is a quadrantal angle. Here's 0, here's 180, 90. I actually still do quadrantal angles the exact same way. If I land on the line, I'm just like, oh, it's a point, negative 1, 0. So cosine is the x value, so negative 1. The way you do with the way you're supposed to kind of do with the table, I still think this is the easiest way to do a quadrantal angle. But the way you're supposed to do with the table is go, okay, I don't have 180, but I do have the thing opposite of it. I have 0. So 0 of cosine is 1, but since it's not 0, it's the opposite of it, you change the sign. So it'll be negative 1. So that's the way you're supposed to do with the table. I just think it's easier to if you fall in a quadrantal angle, just memorize, oh, it's one of the endpoints. And cosine's x. Okay, almost done. Last thing. So this is a little different. It has nothing to do with like special right triangles or a table, but this falls in the unit circle kind of motif. what, and this is one of IB's favorite questions. So what happens here is this. They'll give you a trig function, like tan of theta equals -2/3, and they'll tell you what quadrant it is, or they'll give you some clue about what quadrant it is, and they want you to find another triangle. So the way you do this is you just draw a triangle. Draw given triangle in given quadrant. So here, I'm going to draw tan of 2/3 in quadrant 4. So we want to draw like we always draw it, right? Like this. So we're going to draw a triangle in quadrant 4, like we always do. Here's our reference angle, here's our right angle. It is tan, so I would fill out sides. So maybe I should label these. Fill out sides using SOHCAHTOA. By the way, so the triangle method is the best. So here, right, we have tan of theta. Here's my theta. Right, what is tan? Tan is TOA, opposite over adjacent. So my opposite would be 2, and my adjacent would be 3. Like that. Now, if you notice this is negative, one of these has to be negative. Which one? Keep in mind it's an XY chart, right? You go right, positive, down, negative. So the 2 should be negative. And once you do that, you find the missing side, right? We have a missing side here, but in this case, the hypotenuse is missing. Find missing side using a square Pythagorean theorem. So you gotta find missing side. Pythagorean theorem in this case. Remember, C is always the hypotenuse, no matter what. So in this case, it would be 3 squared plus -2 squared would equal C squared. So 9 plus 4. Remember, when you square a negative, it becomes positive. So I get rad 13 equals C, or rad 13 equals C. So C 13 equals C squared, so C equals rad 13. And keep in mind, hypotenuse is always positive. We're never going to make that thing negative. It's a distance, it's always positive. And then all you do is SOHCAHTOA the triangle. Right, that's basically it. What we're doing here is we're making a triangle with the original one. So we're using this to build a triangle, and once we build that triangle, we're done with it. All we do is find the missing side and then do SOHCAHTOA with what they want. In this case, I want sine. Remember, sine is opposite of hypotenuse, so opposite of hypotenuse. -2 over rad 13. There we go. Let's do one more just for practice. So this one says cosine equals -18 over 7 in quadrant 2. So here's quadrant 2. Right? Quadrant 1, 2, 3, 4. Right, so there's quadrant 2. And then we fill out the sides. So cosine, so SOHCAHTOA. So adjacent for hypotenuse. So my adjacent is 8 and my hypotenuse is 17. Remember, one of these had to be negative, and this one's a little easier because hypotenuse is never negative, so it's going to be then 8. But also we went to the left, so it's negative. And also, we'll talk about this. You can also just ignore that if you want. We could check our answer using all students take calculus when we're done. You can also just do that. We'll talk about that in a second. Anyway, we get this. Right, I gotta find my missing side. So we're gonna do a squared plus b squared equals c squared. Remember, c is always our hypotenuse. So we're gonna get -8 squared plus b squared equals c squared. A and b don't matter, I just made it 8 for some reason. So we get that. So we simplify this. This is 64 plus b squared equals 289. Solve for this to match the 64, so that's 64. B squared equals 225. Square root of that? Hey, 15. So this is 15. Plus or minus? Well, it went up, so positive. But if you don't know that, we'll talk about that. And again, same question is find sine. So sine is theta equals opposite of hypotenuse. So opposite over hypotenuse. 15 over 17. And again, if you don't like the negative part, like it's not working for you, we could always use all students take calculus. We're in quadrant 2 at the end, so my sign should be positive, like I have it here. Over here, right, we finished in quadrant 4, sorry. We finished in quadrant 4, and quadrant 4 only cosine's positive, so the sign I was looking for should be negative. So you can use that to work it. Anyway, that's the lesson.